Okay, so I will be presenting on field trials of microbially induced desaturation, or MID, for earthquake liquefaction mitigation. And I think we're all fairly familiar with our geologic setting and seismic setting here in Portland and the liquefaction hazard that we face. We have seismic sources from the Cascadia subduction zone, as well as local shallow crustal faults as well. And what we're concerned about for this project is loose, young, liquefiable silt soils that are primarily along the Columbia and Willamette rivers. And the concern that those will liquefy in a strong shaking event and cause extensive damage to overlying infrastructure. One area that we're particularly concerned about is the critical energy infrastructure hub, or the CEI hub, located along the Willamette River, where 90% of Oregon's liquid fuel is handled and 100% or all of the jet fuel for the Portland International Airport. These above ground storage tanks of fuel, such as these shown here, are they're extensive throughout the CEI hub, and they're, for the most part, or many of them are founded or located on very liquefiable, loose, young soils. So again, we're concerned that should the earthquake hit and cause damage and liquefaction along the CEI hub, that it will cause the fuel from these tanks to spill, losing that resource for recovery and causing environmental and health damage as well. So we're very concerned about these tanks and their liquefiable soils. So with that kind of motivation behind this, we, in the summer of 2019, performed field trials of MID, or microbially induced desaturation, to look at it as a method for liquefaction mitigation. We did 2 field trials in August and September of that year at 2 different sites. And our objectives of those field trials were to examine MID performance at the field scale, to evaluate its performance in silty soils, since we have so many silty soils throughout the Portland area, and to also study its effectiveness for liquefaction mitigation. We have some just images along the side here of various grad students and researchers working on this, including 2 of our graduate students, Kayla and Melissa. And then at the bottom is the team, the research team, along with researchers from the University of Texas, Austin, who brought out this mobile shaking truck called T-Rex out to the site to test it. And I'll go more into our testing with T-Rex and the results at the end of the presentation. And then one sort of exciting thing about our trials for us was that it was the first field trial of MID for liquefaction mitigation in the US. Similar methods have been used for environmental remediation, but for liquefaction mitigation, it was one of the first looks at it at the field scale. So what I'll be presenting today, I'll go first into a bit of background on MID for liquefaction mitigation, and then I'll discuss the subsurface conditions at both the Sunderland and the Harborton sites, the 2 sites that we did these field trials at. I'll discuss our application of the MID treatment solution, and also present some of our monitoring data and discuss the results of these field trials. Did we desaturate the sites? And then finally, like I said, I'll discuss a little bit about our T-Rex shaker truck results and testing. So going into the background and discussing mitigation of silt soils for liquefaction. We have extensive liquefiable silt soils particularly along the rivers here in Portland. And the mitigation solutions or methods for silts are fairly limited. The primary method for mitigating silt soils is to perform deep soil cement mixing in a grid pattern, which acts to reinforce the soil and keep it from losing strength and deforming. Sort of acts the way that rebar acts in concrete, to keep it and reinforce it in place and keep its strength. I have a video here showing from Condon Johnson showing this method being performed in the field and installing this grid pattern. And what we notice here is that it's quite invasive. And it's not something that could reasonably be performed underneath an existing structure, such as a fuel tank. So given that mitigation methods for silts are fairly limited, and the methods that we do have, such as deep soil cement mixing, are pretty invasive, we currently don't have any economical methods for mitigating silt soils for liquefaction, at least when it comes to those soils beneath existing structures. So what we wanted to look at with this project was at desaturation as a method for mitigating soils beneath existing structures. And a little bit of background on desaturation for liquefaction mitigation. I'll do it over 2 slides and discuss 2 sets of experiments that have been published. So these experiments here that I'm showing on this slide were performed on boxes of loose sand that were saturated and put on a shaking table. So what these authors observed with Hay et al. 2013, we'll start here on the left, which plots these shaking table tests over time on the x-axis, and then the water pressure in centimeters on the y-axis for various points in these boxes that were then shaken. So what we see with this fully saturated sample is that during the time of shaking, from about this point onwards, we see that shaking causes excess pore water pressure buildup within the sample or within the soil. Now, when they repeated that test with soil that was only 95% saturated, so a small decrease in saturation, during shaking, they noticed or they observed that there was much less excess pore water pressure buildup for the 95% saturation test. And then as saturation dropped or was decreased to 80% with the final test, we see even more suppression of excess pore water pressure buildup when you see very, very little excess pore water pressure compared to the fully saturated sample. So we can start to limit the amount of excess pore water pressure that builds up in soil during shaking by introducing or by desaturating the soil. If we take that a step further and look at the actual cyclic strength of the soil with saturation, we look to the O'Donnell et al. 2017 set of tests that were performed on sand with cyclic lab testing, direct simple shear. Plotted here is the cyclic loading placed on the soil, the cyclic shear ratio. And then on the x-axis is the number of cycles to liquefaction when the soil is loaded at that cyclic shear ratio. We see that, and if we look at the bottom curve here, fully saturated soil, like we typically find in the field, we see that it takes fewer cycles to reach liquefaction for a given cyclic loading level. And then as saturation is reduced, just a small amount from 100% to 99%, we see that it takes more cycles or stronger cyclic loading to reach liquefaction. And the soil becomes more resistant to liquefaction even more when that saturation is dropped to 97%. So what we see with these set of experiments, both the last slide and this slide, is that by reducing the saturation of our soil just a small amount, decreases that amount of excess pore water pressure buildup, and in turn we get a stronger soil, more resistant to liquefaction. So with these field trials, we looked at a microbially induced method to induce desaturation in our soils, MID. And the advantage of this method is that it's potentially non-invasive and that it could be applied beneath existing structures. The method, it works by introducing a treatment solution into the subsurface through an injection well, and then having that treatment solution seep and migrate beneath the existing structure or to other parts of the soil, the treated zone. That treatment solution, it stimulates native denitrifying microbes, and they perform a denitrification reaction, and they produce carbon dioxide and nitrogen gas. That gas, for the most part, remains in the soil and displaces pore water, therefore reducing the saturation of the soil. We think that performing this method or using MID on silty soils is advantageous because silts have such small pore space compared to like gravels or sands that the gas may be less likely to migrate out of the soil for a silt and lose saturation. So we think that there's also some advantage there with silty soils. Our picture here on the right comes from O'Donnell 2015, and it's showing an SEM image of 2 sand particles. And then this here is a remnant of a gas particle that was formed by an MID reaction. And we see that remnant of it because we have calcite that precipitated around it. And you can push this reaction further along with stronger solutions to then precipitate calcite precipitate after you get that gas produced as well. But for our project, we were only interested in the gas and the desaturation. All right, so moving on to our field trials. So We performed our field trials at 2 different sites here in Portland. We had the Sunderland site near the Portland airport and the Harborton site just to the northwest of the CEI hub. And this is a picture here of our Sunderland site near the airport, shown by the airplane. And this is it when we were in more or less full operation of our field trials. So fairly small footprint. The site is on Columbia River floodplain deposits, and we found that our soils were fairly uniform, and that they were silt soils with an average plasticity index of about 14. And this was important because it meant that our soils were considered moderately susceptible to liquefaction with this plasticity index. We have a fairly shallow water table at the site. Again, this was in the summer, and our water table was about 1 meter below the ground surface. In the winter, the water table, well, the site floods and it rises above the ground surface as well. And these are just some pictures of the soils at our site, just showing kind of fine-grained uniform soil. The MID treatment that we performed at this site through those injection wells, we ended up treating soils, or we targeted soils to treat from about 1.5 to 6 meters below the ground surface, that interval. The Harborton site in the CEI hub, this is its location here. And these soils were a little bit different. These are Willamette River deposits and a bit of dredged fill as well from the Willamette River. And what we observed is that there's a lot of interbedded non-plastic silt and fine-grained sand with low plasticity silt. And I think this picture here is quite interesting from an SBT that we pulled up. You can see that really, really loose sand and silt here that I'd be quite concerned about in earthquake loading. So, and then at this site, the Harborton site, we treated a smaller interval of soil from about 3 to 4.5 meters below the ground surface. Right, so now moving on to how we applied the treatment solution for our sites. The treatment solution for MID is an aqueous solution of calcium nitrate and calcium acetate. The solution that we mixed was about a 1-to-1 molar ratio of the acetate and the nitrate. And we produced about a 0.06 moles per liter nitrate concentration of the solution. At the Sunderland site, to stimulate that microbial growth, we did add a little bit of Miracle-Gro and Epsom salts to stimulate the microbe activity and get that reaction going. The reaction actually ended up occurring maybe a little bit too quickly at the Sunderland site, but it's one of the lessons learned. And we found that we didn't need it at the Harborton site. These are our grad students that are mixing in one of our totes that are mixing the salts into solution, or substrate into solution. And then I've included this slide here just showing the chemical reactions. This is not my background, but I thought in case anyone is interested in what these reactions are. So we have the denitrification reaction to start off with acetate and nitrate up here. And that acetate and the nitrate, we get the denitrification reaction that produces biomass and nitrogen gas, as well as some bicarbonate. With the calcium that we have in solution from the calcium acetate and calcium nitrate, we may get a little bit of precipitation of from the bicarbonate as well. And then any remaining bicarbonate in solution may form carbon dioxide in the gas phase. So the primary reaction products that we're concerned about with our field trials was the biogas, the nitrogen and carbon dioxide. And then we also had to manage the biomass as well during the injections of the treatment solution and limiting the permeability of our soils, and potentially some bioprecipitate as well. This picture down here of these 2 flasks in the corner is just a little demonstration that we did in our lab when we were starting off with soils from the Sunderland site. We have one that we mixed with the treatment solution, and you can see the gas that produced in the soils there and displaced some of the pore fluid, as well as the soil itself, and then the untreated solution where we don't see that biogas produced. It's worth keeping in mind that this is at like pressures in the lab, so atmospheric pressures, whereas we'll get much more confining stress within the soil that likely reduces the volume of the gas produced. So to apply the treatment solution in the subsurface, we at both sites, we applied the solution through a central injection well, and then had 4 equally spaced extraction wells around it. Into the injection well, we fed the treatment solution both through gravity feed and then with pumping injection as well through an inline pump. And then on this plot, I've just got this this symbol here, and that's where we installed one of our sensor arrays as well for monitoring between the injection well and one of the extraction wells. And then again, we just have pictures of our grad students that are doing the mixing. And so they mix the solution in this tote here, and then transferred it to a larger container that they would then dilute down to the required solution concentration. And this is a picture here from the Sunderland site of our injection well with a little pressure gauge on it, and the pump for inline pumping is just back here. So we had the 4 extraction wells around the injection well, and those helped us to provide water to then mix the solution and re-inject back through the injection well. And they also encouraged migration of the seepage solution throughout the treatment zone. And we assume that the extraction well is about delineated our treatment zone. So it had a diameter of about 3.5 meters. We were concerned that both we had fine grained soils at this site, that we would very quickly draw the water table down, and that our pumps would both run dry, and that we might potentially induce desaturation by drawing the water table down. So we did set up a control system shown here, part of it, where we had a float switch at the top of the screened well interval, so that when the water level was drawn down below that float switch, the pump would shut off, allow the water level to recover, and then it would begin pumping again. So we never drew the water level down below the top of our treatment interval. This is a picture of our Sunderland site, a close-up of it in full swing with our injection well in the middle, and then our 4 extraction wells. This is that sensor array between the injection well and the extraction well. And then we also had these additional sensors here for seismic testing and the T-Rex testing as well. Sorry. So, and then at our Harborton site, we have a very similar setup with the Taro sensors, but without the additional sensor array, since we didn't do T-Rex testing out there. And then you can also see here, we have the solution tank where we mix some of our substrates into solution, and then the tank that we have used to collect our extracted groundwater. So applying the treatment solution at both sites, we managed to do it for about 4 weeks. And we're showing from the time of start of treatment down here versus the treatment injection volume on the y-axis for the Sunderland site and the Harborton site. And so what we see is just looking at it in terms of volume at the Sunderland site, we started off at a relatively low rate where we had to kind of build up and get our procedures down for declogging the wells of the biomass and making the injection relatively efficient. But then after about 2 weeks of treatment, we were able to get a pretty steady high rate of injection into the subsurface. And we see something similar at Harborton, where we had a bit of a slow start, but then took off later on. And then with both sites, we ended up introducing about 60% of the pore volume into the treatment area. We were limited by time and budget, but it was interesting to understand whether this was sufficient to desaturate the site and to achieve this desaturation that we were aiming for, was 60%. So now let's look to the monitoring and our results of this treatment program and the trials. So with our monitoring, we aim to observe changes in saturation ratio in the subsurface, track treatment solution migration, so how it's actually seeping through our targeted treatment zone, and to observe how the reaction is taking place in the subsurface. For the data collection, we used CTT divers, which measured electrical conductivity in the injection tanks and the extraction tanks, and also helped us to monitor the volume of water that was extracted and injected. We used these sensors called Taros 12 sensors where those prongs are embedded into the side of a hole in the soil, or an augured hole in the soil, and then backfilled. And we installed vertical arrays of those sensors at this point here with those Terros 12. And those measure bulk electrical conductivity of the soil water, soil and pore fluid, and as well can help us, and took measurements that relate to the water content of the soil as well. And then we did some seismic measurements as well. At the Sunderland site, we had this array that we could perform crosshole seismic measurements and also instrument the T-Rex testing. We also did seismic cone penetration or downhole seismic velocity measurements and direct push crosshole methods at the Sunderland site for shear wave and pressure wave velocity measurements. Right. So first looking at our CTD divers and the electrical conductivities. So the idea behind measuring electrical conductivity was that our treatment solution was dissolved salts, and those salts increase the electrical conductivity. And so we have quite a high electrical conductivity of our treatment solution. Then as the treatment solution migrates to the subsurface and the microbes consume and react with those substrates, the substrates are converted into either biomass, solids, or gas. And so the salinity or the electrical conductivity of the solution is then decreasing as an indication that the reaction was taking place. So by looking at the change in electrical conductivity, we could understand how the MID reaction was progressing. And so I think it's worthwhile starting down here at the Harborton site, since things behaved a little bit better at the Harborton site. We have the electrical conductivity plotted on the y-axis and the time from start of treatment on the x-axis. The green line, this upper one, is the electrical conductivity of the injected treatment solution, and the blue is the extracted electrical conductivity. And so as expected, the injected, the green, is much higher than the extracted. And we see that about a day into treatment of the extracted groundwater, we go from rather low levels and we get an increase in electrical conductivity. This was an indication that the treatment solution had migrated to at least one of those extraction wells. And for the next about 10 days, we end up with fairly elevated levels of electrical conductivity in the extracted groundwater. And then we start to see that decrease, indicating that the MID reaction is taking place and that potentially we're producing biogas in the subsurface. And then we get low electrical conductivity values for the remainder of the treatment, the field trials at the Harborton site. At the Sunderland site, we see something similar where we have lower electrical conductivity values of the extracted versus the injected water. But what's interesting with the Sunderland site is that we started to see them like talk to each other, where when we started an injection, with kind of indicated by these lines here, is we would take this sensor out, clean it, so electrical conductivity would drop, and then we put it back in, it would shoot up again. When we started an injection, we would see that at least one of the extraction wells, there was almost like a preferential pathway between the injection well and one of the extraction wells. We'd see the electrical conductivity jump up when we started injection and then slowly taper off as the injection continued on and finished. And so we think that, like I said, there may have been some preferential pathway between an injection well and extraction well. And so one of our concerns was that the treatment solution was just being channeled through that preferential pathway and wasn't migrating to the remainder of the treatment zone. So that was something that we were interested in keeping an eye on. Right, so then we have these Terros 12 sensors as well that were embedded in a vertical array at both of the sites. And we embedded them midway between an injection well and an extraction well. And I'll start at the Harborton site again to discuss our results. So we have the electrical conductivity on the y-axis and the time from start of treatment on the x-axis. And about 10 days into treatment, we see that increase in electrical conductivity with these two deep sensors, which was nice to see, which meant that the treatment solution had arrived at those two sensors. And then the reaction was taking place and reducing the electrical conductivity after its arrival. And we see something similar with these other three sensors here, that we get arrival of the treatment solution and then reaction taking place. These sensors, these two actually, these shallower ones, are actually outside the targeted treatment interval. So we did get a little bit of migration of the solution above the well screen level, potentially from just injection pressures or dispersion of the treatment solution. We do see something similar at the Sunderland site as well, where we get an increase in electrical conductivity followed by a decrease, arrival of the treatment solution, and then reaction of the substrate and the MID reaction. But we did have something sort of funny happening with the sensors, almost like a sensor drift happening over time. And that may have been installation issues with the Sunderland site, since it was the first site that we installed and we didn't quite do it ideally as we did at the Harborton site. But importantly, we still see the increase in electrical conductivity that the treatment solution did arrive at those sensors. The Terra sensors as well, they measured electrical capacitance that relates to the water content of the soil. So what we saw at these sites, at both of these sites, is that this electrical capacitance water content relationship indicated a decrease in water content over time for both of those sites during and after treatment. And what's valuable about that is that those water content measurements can then be related to a change in saturation. So, and of course, saturation and reducing the saturation is what our target was for these field trials. So if we assumed an initial saturation value, either fully saturated or close to it for the shallower soils, we could relate those water content changes to a change in saturation. And we see that at the Harborton site, saturation potentially reduced to about 90 to 95%. And at the Sunderland site may have reduced from anywhere, it looks like 70% to about 95% as well. And going back to the background on liquefaction, that reduction in saturation can be enough to increase the resistance to liquefaction and increase the cyclic strength of the soil. We also did take some Shelby tubes, or just samples of soil from both the sites after treatment. And we measured on those soils quite low saturation values, which was encouraging that saturation was reduced. But it was quite low, which we think is just because it's difficult to measure saturation on soils, because when you bring the soil up to atmospheric conditions, you get gas expansion of the soil and potentially loss of moisture as well during the sampling process. So our last method of monitoring was seismic velocity, or seismic pressure wave velocity measurements. And the idea here is that when soils are fully saturated and you measure P wave velocity through them, or pressure wave velocity, you're measuring the pressure wave velocity of water. And so you tend to get a fairly high P wave velocity for fully saturated soils. Then as the P wave velocity drops just a small amount, we see a very large decrease in P wave velocity that accompanies that. And so on this plot here, which is plotting degree of saturation versus P wave velocity, we see that decreasing saturation from 100% to even 95%, we drop a P wave velocity from over 1800 meters per second to around 500 meters per second. And there's similar reported values for fine grained soils with the saturation greater than 99.5%. We have a P wave velocity of about 1600, and then reducing saturation below 98.5%, we end up with a P wave velocity of 400 meters per second. So this was valuable because if we could measure a drop in P wave velocity, we could then say that that indicates that we've decreased our saturation. So to do this, we had a Crosshole seismic array at the Sunderland site. We have seismic sources that are located at a certain distance from our geophones that are a distance apart. So we could send a seismic wave or a P wave down the sources and then measure the difference in arrival times between the geophones at the site. This is just images of our graduate student performing these tests with an instrumented hammer. And here on the right is the seismic source. So what she's hammering to send the wave down into the ground. And so by performing these crosshole tests regularly throughout the treatment and then after treatment, we can look at changes in our P wave velocity. So plotted here, P wave velocity and the time since the start of treatment for the 4 depths that these crosshole values were taken at. We see that we have 2 that start at very high P wave velocity values, indicating nearly full saturation. And these are our 2 deepest sensors, 2.5 and 4.5 meters. And about midway through our treatment, about 10 days into the MID treatment, we do see that strong decrease in P wave velocity, indicating that at this crosshole array, about 10 days into treatment, our saturation dropped below 98.5%. And then we've continued to go out and to take these measurements and to monitor the P wave velocities since the end of treatment. And it does show that the saturations have remained below 98.5% since the end of treatment and through two wet or rainy seasons where we get flooding at the site during the winter. And so we've managed to see sustained desaturation during that time too. We also have P wave velocity measurements from various locations in our treatment zone. These were performed with downhole tests through a cone penetration and also through direct push crosshole. So starting here at the Sunderland site with our P wave velocity versus depth, this line here is pre-treatment with direct push crosshole. So high resolution tests of our P wave velocity profile. And we see that above or below about 2.5 meters, it indicates that we have very high saturation. This solid black line here was taken with the seismic CPT, so a downhole seismic test. Again, we do see that we get a strong increase in P wave velocity with depth, but it is still a little bit lower than those direct push crossholes. It just comes down to that we get quite a bit of wave attenuation since the source with the CPT is at the surface. So that's what we attribute these lower values to. But what was valuable about this is that with the CPT is that we could go in and quickly perform tests after treatment at various locations in the treatment zone. And that would be these blue lines here at the low P wave velocity. So relative to the pre-treatment values or the pre-treatment profiles, we do see quite a decrease at these 3 different locations in our treatment zone, indicating that we had a decrease in saturation at those locations. And interestingly, we pushed one outside the treatment zone, about 3.5 meters outside of it. And we also saw relatively low P wave velocity values, indicating that we may have had some treatment solution migrate beyond those extraction wells, which sort of makes sense now looking back at it. We saw similar results at the Harborton site, that between our initial profile with elevated P wave velocity values, we saw a decrease in P wave velocity for 2 locations in the treatment zone, and then another location outside the treatment zone as well. So from this data, we can sort of indicate that we had migration of the treatment solutions throughout the treatment zone, even though, as you remember at the Sunderland site, we may have had a large preferential pathway that we were concerned about. The final bit of data that we collected is X-rays of our sampling tubes. So through X-raying our tubes, we could get a better sense of the structure and any gas pockets that had formed in them. The image on the left is a sample that was taken pre-treatment, and then with post-treatment on the right, we can see maybe some gas pockets that formed from the MID treatment at the Sunderland site. So a bit of a summary of our monitoring data. The data indicated that we did decrease the saturation in the treated soil, which was positive. That was what we were hoping would happen with these field trials. The BP measurements indicated that saturation dropped below 98.5%. And the in situ electrical capacitance measurements indicated potentially a larger decrease in saturation based on changes in moisture content. And then we also took soil samples as well that we saw a saturation decrease, but like I said, difficult to measure saturation on sampled soils. And our treatment solution likely distributed throughout our targeted zone for treatment. We had in situ electrical conductivity measurements in the treatment zone. That's all the arrival of the treatment solution and reaction of it as well. Profiles at various locations in the treatment zone indicated that we had reduced the P wave velocity. And this in spite of seeing that we had subsurface heterogeneities in our treatment zone that were potentially channeling the treatment solution. And actually what we think happened was treatment solution may have been initially channeled through these heterogeneities, but then as the reaction takes place and biomass builds up in those heterogeneities, the permeability decreases and the treatment solution ends up migrating to other areas. That's just a hypothesis that we're working on and planning to look at further. So finally, discussing our T-Rex in situ cyclic testing at the Sunderland site. We did this shaker truck testing 2 times, one pre-treatment in July and then once post-treatment in September. And we wanted to compare the changes in the cyclic response, particularly that excess pore water pressure buildup, and see if we had any changes in pore water pressure pre-treatment and post-treatment. So this is a picture of our shaker truck, or the T-Rex shaker truck from University of Texas, Austin, and it sits on top of the sensor array and then shakes the ground and transmits seismic waves into the ground. This is the same array that we use for the Crosshole seismic monitoring. So now these geophones, they create, they measure the strain, or you can back out the strain based on the accelerations, and through the strain or the displacement at each of these geophones then relate to the 4 geophones almost like a finite element. And we can assume a strain level within this element and then relate that to the pore pressures that develop at each of those pore pressure transducers in the middle of the element. And the T-Rex base plate sits on top and then shakes the ground and transmits that seismic wave. So this is some of our data that resulted from the T-Rex shaking with the excess pore water pressure ratio on the y-axis and the time, including the time of shaking shown here on the x-axis. And so we're comparing the response of the untreated soil, which is the blue line here, with the treated soil, which is the red. And typically the results of T-Rex shaking are interpreted as the excess pore water pressure at the end of shaking, in which case we see that we actually had more excess pore water pressure for the treated than the untreated, which was unexpected, although there's still very, very small amounts. But then looking at what happens afterwards with the pore water pressures that develop after shaking, we see that there is a suppression potentially of excess pore water pressure, where we get reduced excess pore water pressure in the treated zone than the untreated. These weren't quite the results that we were looking for or we're expecting based on the end of shaking. And it may have been due to our very small strain levels that were imparted with 0.12% for this case. And if we then further tested our soil and looked at it at larger strain levels. And so if we look at the T-Rex shaking here with the cyclic strain on the x-axis and the pore water pressure on the y-axis, this is our T-Rex shaking and the resulting pore water pressure ratio. So we get small strains and in return, small excess pore water pressure generation. Through lab testing, which would be these blue symbols and then the squares as well, we see that it takes more strain on the soil to produce larger amounts of excess pore water pressure. So we think that ultimately the T-Rex shaker truck wasn't imparting large enough amounts of strain on our soil to produce meaningful excess pore water pressures that would then be suppressed by the MID treatment. So this is something that we're continuing to look at with laboratory testing and potentially future field testing as well. So our conclusions on future work, we treated 2 liquefiable silt sites with microbially induced desaturation. And the data seem to indicate that our targeted soil stratigraphy was successfully desaturated. Pressure wave velocity measurements indicates desaturation through the treated layers. And it's also supported by soil sampling and moisture content measurements. Electrical conductivity sensors showed that our injected solution migrated throughout the targeted soil as well. We did see that there's treatment solution through preferential seepage paths, but then also non-preferential pathways as well. And we did see with TRX testing some reduction of post-shaking pore water pressure values, but we are performing more work with regards to that. So looking forward to the work that's continuing with our lab, we'll be looking at how effective MID is for liquefaction mitigation of silt soils. So performing lab testing, cyclic testing at various saturation levels of different silt soils, like those from the Sunderland site. We're also interested, and this is important for applying this method in practice, is just how long will it last? So understanding how long that desaturation remains in the ground. Our graduate students are still going out and performing those crosshole measurements, which will get us a couple years of data in the end, and taking soil samples to look at saturation measurements. But to really look at long-term over like the lifespan of a structure, we do think that we'll need to be doing both physical modeling and numerical modeling as well to extend the time period out years and years to look at saturation. And then we're also interested in looking at how subsurface heterogeneities affect the treatment solution distribution and saturation distribution. Like, are we effectively mitigating liquefaction if we have saturation reduced here, not here, but here as well? And so that's one of the questions that we'll be looking at. So to do that, for now, sampling and an analysis of treated soil and groundwater to look at any discrepancies or spatial variabilities. And then as well with numerical modeling of the bioreaction and transport too. Acknowledgements of this work with collaborators from University of Texas, Austin, Arizona State University, and my colleague Arash Khosrabafar in the Civil Engineering Department as well, and graduate researchers and support that we got from folks here in Portland and consultants and agencies as well. And with that, yeah, happy to take any questions.